Hi, this is Maggie from Design Code Debug Repeat. Welcome to the channel. This video and the others in the Chapter 6 Problem Solving with Python playlist are an introduction to the concepts you will need to write programs with lists. This video accompanies Problem Solving with Python Chapter 6, but it's okay if you don't have the book. The videos stand alone as instruction on these topics. In the last video, we talked about using a loop to iterate over a list, visiting and processing every element, and we revisited some of our loop algorithms. In this video, we're going to talk about how lists are stored in memory, which will help us understand why, when we copy a list of lists, both copies might point to the same elements. Let's dive in. When we assign a value to a name with an assignment statement, Python assigns the memory address of the value in memory to the name. So if I have the code x location equals 100, y location equals 200, numbers equals 1, 2, 3, 4, these might be at memory locations 1843017026896, 1843017030096, and 1843027087680, and these are the values assigned to the variable names. When we assign a value to a name with an assignment statement, Python takes the memory address of the value and assigns it to the name. You can imagine this as arrows pointing from the name to the value in memory. You might wonder why the value isn't just assigned to the name, rather than taking this extra step of putting the value somewhere else in memory and assigning that memory address to the name. It is not possible to always know, when a program is written, how much memory it will need for each variable while it's running. For example, if we ask the user for their name, we don't know if their name will be short, like Anne, or longer, like Juan Carlos, or very long, like State of Rhode Island and Providence Plantations. If we ask for a list of their favorite movie titles, they might not have any favorite movies, or they might have 5, or they might have 100. Python manages this by having a large block of memory that can be allocated as needed as the program runs. This memory is called the heap. When we look at the code of a program, we can see all of the variable names that are defined for each namespace. This is all of the names that appear on the left side of an assignment statement. The memory for all of these names can be set aside before the program executes, because each of these names is the size of a memory address, such as 1843017026896. For example, 4 bytes or 8 bytes. But what they reference could vary in size, so that data is allocated in the heap. Now, I am going to focus on lists in this video so we understand how it can feel like they're treated differently from other data types we've seen so far. If you want to understand more about how Python handles memory allocation, you can look at the memory management documentation on python.org. I'll include a link in the description. You can also ask me questions in the comments section of the video. Let's draw some pictures of some code so we can first get a sense of how this works. In this program, called memoryexample.py, I have annotated 3 list variables containing integers: dice, also dice, and copy dice. Dice is initialized to the list 65125. We might draw a picture of memory that looks like this. We have in our main or module namespace a variable dice represented as a box. And in our heap, which I generally draw sort of like a cloud because its management is handled by a memory manager, so we don't know exactly where anything is going to be, in the heap we have our usual representation of a list as a box with locations for each value, with the values within in order, and we have an arrow from the dice variable pointing to the list representation in the heap. And I'm going to use that representation for the list in the heap, although technically it's more like this, which I think contains a distracting level of detail. So technically each integer is also somewhere in the heap, and the dice list actually contains the memory locations of those integers. And there is only one of each integer, so both 5 locations in the list contain the same memory address. We will simplify this because I don't think it's helpful to represent this level of detail at this time. Now below that we have 2 lines of code, also dice equals dice, and copy dice equals dice.copy. Let's draw a picture of each. So 2 more boxes over in the main namespace for also dice and copy dice, where the arrow from also dice points to the same list in memory as dice, and the arrow from copy dice points to a copy of the list, a whole separate list with the same integer values. This offers a visual explanation for why changes to dice will change also dice as well and vice versa, but changes to copy dice impact only copy dice. But, as I said in earlier videos, this is only true if we have a list of numeric types or strings. If we have a list of lists, a copy is only what we call a shallow copy. Now, I haven't talked about solving problems with lists containing lists yet, but I think we can still understand how memory works without talking about how to solve problems with lists within lists. In a later video, we'll go into more detail on when you might choose lists of lists as a solution and how to iterate over them. For now, let's look at this program, listsoflists.py. Here I've annotated two variables of type list int. Dicebags is initialized to open square bracket, 6, 5, 1, 2, 5, close square bracket, comma, open square bracket, 1, 1, 3, 4, 6, close square bracket, close square bracket. So that's a list containing the list 65125 as its first element and the list 11346 as its second element. And we have the code copy dicebags equals dicebags.copy. I might draw that this way in memory, where I have my two boxes representing the variables in the main namespace, dicebags and copy dicebags. And those two boxes each point to lists in the heap, but those lists have arrows pointing to their enclosed lists. And those enclosed lists are the same lists. So in other words, I have two lists in the heap, 65125 and 11346, and both dicebags and copy dicebags, while they are separate lists themselves, point to these two lists. Why is that? Because dicebags was copied to a whole new list, but that meant copying the contents of dicebags, which is the memory addresses of its list elements. This is called a shallow copy, because we copied the list, but we didn't go as deep as we could and make copies of what's in the list. That would be called a deep copy. Let's look at two changes I might make to copy dicebags, one that impacts the original list and one that does not. First, the change that does not impact the original list. Look at the lists in memory. Suppose I change the element at index 0 in copy dicebags to a whole new list. In code, that might look like copy dicebag sub 0 equals the list 11111. Because copy dicebags is a separate list from dicebags, I can assign to an index so that it points somewhere new, and that has no impact on dicebags. That, of course, looks like copy dicebags' first pointer pointing to a different list in memory. It has no impact on dicebags and its two elements. Now, the change that does impact the original list is if I change the list within the list. Because dicebags and copy dicebags are both pointing to the list 11346 in memory, if I change the 3 to a 5, for example, it will be changed for both lists. That looks like copy dicebag sub 1 sub 2 equals 5. I know you haven't seen that indexing before in these videos. Copy dicebag sub 1 refers to the element at index 1 in that list, which is the list 11346. And so we can then index into that, because it's a list, using sub 2, which is the 3, and we can change that to a 5. Now, until this makes perfect sense for now and in future videos, I recommend you draw pictures of memory as you work with lists of lists, and also lists being passed as parameters to functions, as we'll see in the next video. The website pythontutor.com is an excellent resource for visualizing the way lists are stored in memory as well, so you can confirm your drawings by running your programs there. Now, I called this code copy dicebags equals dicebags.copy a shallow copy. How do we make a deep copy? That will depend on what your list looks like. For this list, which is a list of lists of integers, a deep copy would look like, in our visual representation, copying the list and then copying each of the sublists so that the new list pointed to the new sublists. In code, we can make our shallow copy and then iterate through the shallow copy by index, copying each of the sublists and pointing to those instead of the original lists. That way, all of the data in the new list has been copied, and we can change it without impacting the original list, and vice versa. If your structure is different, for example, if you have lists of lists of lists, you'd have to write code that does an even deeper copy. Okay, that is a lot. You may want to read the document on Python memory management or watch this video more than once. I think the best practice would be to redraw the pictures from the code and make predictions about how assignment statements will impact one or more lists. I've included an auto-graded exercise in the description of this video, so you can practice matching copying code to its description. Once you've mastered the concepts here, you're ready to move on.